I'm a cosmologist in the School of Physics, and what I'm actually going to talk to you about today is a book that I had published earlier this year, and the book came out just as the COVID-19 lockdowns were taking off. And this talk that I actually have is one that I put together for essentially a book tour to people interested in physics that I was going to give in the UK and then also later in the US. But that book tour got cancelled. So I have a talk, and I've only had a few people to give it to. So I thought we would open this session by me talking about this book. It's a book on cosmology aimed at almost a layperson, a person interested in physics. It is not going to be at a very high level in terms of mathematics, etc., but we are going to cover some of the key concepts. So what I'm going to do, first of all, is give you a motivation on why we wrote the book, and then I'm going to talk about several of the key physical aspects that we touch on, and why we call this the Cosmic Revolutionaries Handbook. So, I mean, first things first, of course, being a cosmologist, being an astronomer, I have to show one of these obligatory pretty pictures. And this is, of course, an image of the universe that you get when you take something like the Hubble Space Telescope. You point it at a seemingly empty patch of sky, you integrate for many, many hours over days, and this is what we see. So when we peer out into the universe, we see that our sun is in something known as the Milky Way galaxy, and it inhabits this patch of the universe with roughly 200 billion other stars. But when we look out deep into the universe, we see that our Milky Way galaxy isn't alone. And we have of order 100 billion to a trillion other galaxies out there in what's known as the observable universe. So we've got this beautiful picture of the sky. I mean, these images are always beautiful, but of course, as physicists, we don't want to just take pictures. We want to actually understand how the universe operates. And as a cosmologist, my goal in my research is to try and understand the evolution of the universe from the time that it began to today. And cosmology has been one of the great successes of the last 100, 150 years. So this is the kind of picture you get if you pick up a textbook and you ask about what's the evolutionary history of the universe. This is the kind of picture that we now have. We have that the universe was born roughly 14 billion years ago in an event called the Big Bang. There was a period where the universe underwent this rapid burst of expansion in the very early periods, known as inflation. And we know that the universe came out of that state being very hot and very dense. So we had all the fundamental particles buzzing around. They were bathed in a large amount of radiation. But as the universe progressed in age, it continued to expand. And in that expansion, the universe cooled down. You get to a point roughly 1 second to a few minutes after the Big Bang, and the universe actually cooled down to an extent where the first nuclei of elements formed. The universe continued to cool, gravity does its things, matter gets pulled together, and you form stars and galaxies, and you end up with that rich picture of stuff that we can see around us today. So for me, I'm always amazed that in cosmology, we talk about timescales of billions of years, but also talk about timescales of minute fractions of a second, because this is the range of physics we need to consider, and we can put together this picture of a universe evolving over this roughly 14 billion years. So while cosmologists might be slapping themselves on the back, not everybody is happy with this picture. And we sort of get this all the time. I mean, you don't have to hunt very hard on the internet to find places where people will be talking about how cosmology is wrong, okay? So there are always like news stories and blog posts about how cosmology is wrong, how this picture we have about the universe is wrong. And there's actually an entire almost sub-community of people out there who are focused on this notion that cosmology is essentially that we're a bunch of self-deluded idiots who don't understand the way that the universe works. And again, you don't have to hunt around too hard to find this. There are people that propose alternatives, okay? So one of the big ones is this website that I've got here. There's a whole bunch of these. Something called the electric universe. This is something that grew out of some thoughts by Hans Alphen, one of the people that understand how plasmas work, that in fact the dominant force in the universe, according to these people, isn't gravity, it's actually electromagnetism. And that all of the things that we can see out there are shaped by electricity and magnetism and not gravity. And again, they say that we're deluded. And one of the things that you have to deal with as a cosmologist is that the public write to you. The public send you messages. And in fact, I actually have one here that was sent to me. I got this just the other day. This is from somebody who has their own theory of the universe, and they want to tell us that we're wrong and that they have the correct answer. And so this little example I've got here, some of you may have already received emails of this particular person. He's well known in the Australian community for emailing all kinds of people from grad students all the way up to Nobel Prize winners to constantly try and point out that something is wrong with our picture of the universe. And this person here is focused upon general relativity, how we have general relativity wrong, because he has it right, but everybody else has it wrong. And this is an email that he sent to me last year, also CC'd to Westminster Abbey to complain about the equation that was listed or written on Stephen Hawking's grave, right? Because Stephen Hawking talked about black holes. This person thinks that we have gravity wrong and that there are no such things as black holes. So it's, as I said, it's actually a rather big sort of sub-community. And you could sort of say, well, you know, fair enough that they do what they do. Maybe we should just ignore them and let them get on. But the problem that we have is that the public face of cosmology is that cosmology is continuously in crisis. It's not that cosmology is this great success, it's that it's something that is in crisis and needs to be fixed. And my co-author, Luke Barnes, who's at University of Western Sydney, and myself, we give a lot of public talks. And at the end of those talks, there are always people who approach us and they talk to us about the fact that cosmology is in crisis and that they have themselves their own alternative, which they think will fix the universe. If we only listen to them rather than relying on Einstein's general relativity, then we would understand the cosmos. And we basically have the same conversations with them over and over again about how cosmology is actually a success and what they should do if they really think they have an insight that we haven't spotted. So our book essentially is a guide for those people. If you have an alternative cosmological model, what is it that you do to get cosmologists to sit up and notice? Okay. Now, of course, this doesn't only apply in cosmology, right? Quantum mechanics gets the same kind of subculture of people talking about how quantum mechanics is wrong. So it's really, how should you approach a problem as a scientific problem, and how do you solve it? And actually, sending random emails to professors or ranting on the internet is not necessarily a well-proven method for getting your theories across, okay? So that's what our book was about. And so we actually start with the very basics and we sort of build our way up. And what we found is that you even have to explain the process of science to a lot of these people, okay? They do not have a concept of how science works. What are the steps that you do to get your theories and ideas into the consciousness of other scientists? And how are you going to be taken seriously, okay? So as I said, this is not going to be at a super high level, but I said there will be some deeper concepts, and I'll be happy to take any deeper questions people have. So the starting point, I think, for a lot of people is explaining how science works, okay? And the analogy that we try and start off the book with is that you come up to a crime scene and you observe, the crime. Maybe money has been stolen, or there's a body on the floor, etc. And so you treat that observation, that is a fact, that is an observation about the crime scene or the universe, right? And that is what you collect on your telescope if you're observing the sky. On the flip side, of course, we have this notion of a scientific theory. And of course, we already run into the problem that theory in the mind of the general public can often mean speculation or guess rather than the way that a scientist means it. And of course, what we have here, a theory is a complete scenario that can explain the facts that are in front of you, okay? And so if you want to solve a crime, this is what you need. You gather your evidence and you come up with your theory of what explains that evidence. And of course, one of the things that, again, is not fully present when you talk to the public about this, is that there can be competing theories to explain the same facts. So in science, especially when you have science at the cutting edge, you will have a set of observations, but you may have 100 different theories that are trying to explain those observations. And anybody who's worked in particle physics recently know that there was the diphoton result from CERN, and there were hundreds of theory papers to try and explain this one set of observations. We currently have the same situation in cosmology at the moment. We have something called the Hubble tension, which is a set of observations that don't seem to be easily explained with regards to our simple ideas. And again, there are a whole set of competing theories that people proposing to explain those observations. And of course, the scientific method is that you take your theories, you look at your consequences, and you find some more observations. So that's the way that we sort of want to think about observations and how science works. So for cosmology, right, the key two things are facts or observations, right? Things that we observe about the universe. And then theory or theories are ideas about how the universe works. And again, we find that often these two things are blurred in the public mind. And I think part of that comes across from the way that popular science is written, in that the discussion about what is the thing that arrives at the telescope and what is the thing that you make up to explain that observation just get blurred in the writing. But this is essentially what we want to boil down to, is that we have observations, we have collected light from our telescopes, etc. And we've got those observations stretching back for hundreds of years. And your idea about how the universe works better be able to explain these observations that we have. Now, again, as I said, it might seem obvious that to you that this is the way that science works, but to a lot of people, it's not clear. So that's sort of like our starting point. Now we get to the point where why people are unhappy with our cosmological model. And of course, our cosmological model is this thing called the Big Bang theory. And anyone who knows the history of cosmology will know that this name was given to this idea by Fred Hoyle in the 1950s. And he named it as a disparaging term. He actually thought that this idea of the Big Bang, and we'll come to what that means in a moment, was wrong. And he proposed an alternative theory. But the name stuck. So we have this idea that we have this cosmological model, which is the Big Bang theory. And where people get angry is because this theory is weird. And of course, like a lot of good science, it's weird because it's so different to our sort of common sense expectations. So the key things in the Big Bang picture that we have is that our universe is in this expanding space, right? So we started in this thing called the Big Bang. The universe has space which is expanding and things are moving apart. We have in there that space itself, or space-time, can be curved and distorted. But to make our model universe work, we've got some strange ingredients, okay? So the two key ones for cosmology is the universe is made effectively of dark matter, which is roughly 30% of the universe, and dark energy, which is roughly 70%, with normal atoms, the stuff that we're made from, comprising just a small fraction of the energy density in the universe. We also have this leftover radiation, which we'll come to again later. We have galaxies where they're all moving apart, all this kind of stuff. And there's a whole host of things in here which are ideas that people don't like, okay? So the notion of expanding space, people don't like, okay? They sort of say that at some level, they accuse us of hero worship, that we worship at the altar of Einstein, and we take this picture in as if it's almost a biblical or religious text, rather than it really being a mathematical description of the universe. Similarly, the notion that the universe had a beginning, that there was a point 14 billion years ago where the universe was born, other people object to. How could we conceive that our universe was born from this as effectively nothing and expanded into the universe around us today? So they propose alternatives, okay? So often the alternatives that people will come up with are more based in words and pictures than they are in the language which scientists are used to, of course, which is the language of mathematics. And this is where we start to struggle in explaining to them what their theories need to be if they want their theories to be taken seriously, okay? So what I'm going to do on the remainder of the talk is I'm going to just basically jump through some of what I think are the key facts, the key observations that if you were a potential cosmic revolutionary, that you have to be able to explain, okay? So you have to be able to explain observations about the universe, some of them relatively simple, some of them more complex. And you have to be able to explain it at least as well as the Big Bang Theory does. And quite clearly what you want to do is, if you want to have a revolution, is you need to go one step further and have a better theory. So again, if anyone's done some history and philosophy of science, the first one is a well-known one, and that is that the night sky is dark, right? Which seems like a rather obvious kind of statement to make. But this was one of the earliest sort of realizations that people had that started to form our modern cosmological model, okay? So let's just take that fact. That's the observation, right? At night, the sky is dark. Now, let's take ourselves back a couple of hundred years and think about how we might think the universe is structured. You might think that the universe is infinitely large, and you might think that it's filled with stars in all directions, and you might think that it's infinitely old, right? So, Newton had this picture that the universe was a static, unchanging place. It had been around forever, filled with stars. Even Einstein started off his vision of cosmology with the same picture that Newton did, that the universe was static and then changing. So infinitely large, filled with stars. What does that actually mean? So let's just take a look at that. So here we have the Earth, not to scale, of course, surrounded by stars. And of course, what we have is that we're looking out into the universe. And so we have lines of sight that stretch out into the universe. And every so often, that line of sight will land on a star, and that's where we see a star on the sky. But other lines of sight will pass between the stars. And we can go further. And again, along this line of sight, we see no stars. But eventually, okay, if we go far enough, if our universe is infinitely large and is filled with stars and is infinitely old, so light has had time to travel everywhere, eventually this line of sight will impact onto a star. And you can, I mean, it's not difficult to calculate this, right? You eventually will get that the fact that as you go further, the stars are smaller on the sky, but the further you go, the more of them there are because the volume is larger. Eventually your line of sight will land on a star. And so what that means is that essentially every line of sight that you have will eventually land on a star. And if you basically calculate what that means, is that your night sky should be as bright as the surface of a star. Okay? So this is something known as Olber's paradox, is that why isn't the night sky as bright as the surface of a star? And of course, what we've got is that we started this by proposing a theory, a model for the universe. That the universe were, if it was infinitely large and filled with stars, static and infinitely old, then the entire night sky should look as bright as the surface of a star. So that tells us that at least one of these assumptions in here must be wrong. Okay, this is not a good model of the universe because it would predict that the night sky would be infinitely bright. We see it as dark. So something here is wrong. And what we know is now that in terms of the Big Bang picture, the notion that it is static is wrong. The universe is expanding, right? So stars are moving away. And we know that the universe isn't infinitely old. So there hasn't been enough time from light from the most distant stars to reach us. We're only seeing a small sort of illuminated patch around us in the universe. So this is actually important, right? And again, your scientific theory has to have a mind of its own. It has to make predictions, and those predictions must be about everything we observe about the universe, right? So if you come up with a theory and somebody comes up to you and says, well, what does the night sky look like in your theory? You better hope that it says that it's dark, right? And again, as I said, this is an important aspect that many people don't consider. What they do, of course, is they tend to come up with an idea that can explain one piece of information about the universe, the red shifting or something like that. We'll get to that in a moment. Rather than thinking that your theory has to be able to explain the observations of the universe. So that's lesson one, theory has a mind of its own. So lesson two is what we actually see, okay? So I don't know if you have seen these stock images that you can do. It's always embarrassing when you look at stock images of an astronomer because they're always sort of like standing next to a telescope, wearing a lab coat. I don't even own a lab coat, and pointing at, basically where space is, right? So this isn't the way that we do astronomy. We have bigger telescopes, we don't wear lab coats, and we tend not to point at the sky so much. But one of the most important observations for modern cosmology was made in the 1920s by Edwin Hubble, and that's to do with the redshift. So the redshift of galaxies. Now again, I'm not 100% sure who the audience is, so I'm going to go through a couple of things just to make sure we know what we're talking about. What we have, of course, is that we know that we're receiving light from distant objects, and that light is made up of a mixture of electromagnetic waves of different wavelengths. And what you have, of course, is that blue light has short wavelengths, red light has longer wavelengths, you've got ultraviolet and infrared either side of that. But what we essentially are receiving in our telescopes are these electromagnetic waves, right? So radio telescopes get radio waves, optical telescopes get optical light. And what we have is that, of course, when we take a picture like this picture we've got here, you can see that there are colors in there, but those colors are reconstructed by gathering up the blue light, the green light, and the red light, and you squish them together and you make a colored image. So that's very important because the colors of objects tell us a lot about the stars that they contain. I know that places that have hot young stars, they tend to be blue, and you can see there's some blue galaxies in there. Galaxies which have older stars, they tend to be red. So you can see that there are red stars there. But the other thing that we are interested in is not just the colors, but the detailed distribution of light that we receive. So what we do, of course, is we take that light, we disperse it with a prism, well, a grism as it's known, which is similar to a prism. It splits light into its rainbow of colors. And the thing that we're interested in is this thing called the spectrum, right? And again, I know that many of you know what a spectrum is, but what I've actually got here, this is actually some research. This is real research. I'm part of a program called AusDes, which is the Australian Dark Energy Survey. And what we do is we collect light from galaxies, and we look at their spectra. And what we've got here is, if you look in green, this is the light that we collected with the Anglo-Australian telescope at Coonabarabran. You've got blue light on the left, you've got red light on the right, and the green is the light that we've collected. And you can see that this isn't just a nice smooth distribution of light. You can see that there are regions which have got absorption lines, and there are regions which have got emission lines. And these, of course, are a signature of the chemical elements that are in the stars in this galaxy, right? So if you've got calcium and you've got hydrogen, etc., you will get a particular barcode of features which allow you to measure the elements that that galaxy contains. In red on the bottom, that is the spectrum of a galaxy which is basically very nearby to our own. So you could take this as essentially the kind of spectrum of light you would get in a laboratory. If you took some gases, you mix them up and you put sparks through them, it would emit light, and you could also get absorption of that light. And what we've got here is, if you look at the red spectrum, there are some emission lines and there are some absorption lines. But the red spectrum, the features in the red spectrum are not aligned with the features that you see in the green spectrum, okay? So the observation of the galaxy on the sky has its features at different wavelengths to basically our laboratory spectrum. But if I shift my laboratory spectrum towards the red end of so I move it towards the right, when I get to a particular point, you can see that then suddenly there is a really good agreement between the absorption lines and emission lines in my laboratory and the absorption and emission lines that I see in my, my distant galaxy. So what I've had to do is I've had to shift the light to the red side of the spectrum. So this is a key observation again, is that when I look out into the universe and I see galaxies, I will see that their light is red shifted with respect to our Milky Way galaxy, okay? Now there's another key feature from Hubble, and what he found is that the more distant the galaxy, the more the light is shifted towards the red part of the spectrum, okay? So this was his key observation. He was expecting maybe to get a mixture of red light and blue light, so red shifting and blue shifting. But what he was finding is that every galaxy he looked at, the more distant the galaxy, the more its light is red shifted. Now, again, it's important to remember that these are the observations, right? No interpretation yet of what these things are, or what it's telling us. But essentially, if you were Hubble, you come up with a picture, something like this, that you have distance on one axis, redshift on the other, and the more distant the galaxy, the more the galaxy is redshifted. And this is the result that many say Hubble should have won the Nobel Prize for, but apparently astronomy back in the day wasn't considered a real enough science to be awarded the Nobel Prize, so he never got that one. Now we need to start to think about interpretation, right? What is this distance versus redshift telling us about the universe? Now, the redshift can be interpreted in a couple of ways, but one of the key ways, of course, is that one way that you get to shift waves is through, basically the Doppler shift, right? So what you've got here is, this is just straight from Wikipedia, The Doppler shift, of course, is something that you get with sound. And then if you have, was that a question? No? Okay. The Doppler shift is something that you get with sound. And so if you have an ice cream van playing Greensleeves, as it approaches you, the pitch of the music is higher because the waves get squashed together. And as it drives away from you, the pitch is lower because the waves get spread out. And you get exactly the same sort of thing happening in light, that if you have a source of light and it's moving away from you, the light gets stretched towards the red end of the spectrum. If that light source is moving away from you, moving towards you, you get a blue shift and things are pushed to shorter wavelengths. So Hubble's conclusion was that galaxies are moving away from us, and they're moving away from us with a speed which is proportional to their distance. So you double the distance, you double the speed which a galaxy is moving away. And in fact, we can come up with a very simple picture. So this is the kind of picture that we have. So this is the picture that you would have in the Big Bang picture. The Big Bang picture says is that space is expanding, so the space between objects is expanding. And what you get is that as space expands, then things nearby move slowly with respect to you, but things further away move faster and faster and faster. So, and one of the other things which is kind of cool with this kind of picture is that, let me just do it again. If you imagine yourself on any of these dots other than the one at the center, you see that you all see exactly the same thing, right? So what this tells us is that if we could transplant ourselves to another galaxy somewhere out in the universe, and we do the same experiment as Hubble did, that we would see all galaxies moving away from us in exactly the same way. So we're not at the center of the universe in this picture, all galaxies are similar. So the Big Bang picture works well with this, but it's important to note that especially soon after Hubble's results and into the 1940s and 1950s, that there was more than one contender, right? So we have our picture, which I just mentioned, which is our Big Bang theory, where expanding space, and it's that expansion of space which carries galaxies apart from one another. But we have to live with the fact that in this picture, that the universe was smaller and denser in the past. And if you wind the clock back, we had this beginning, which we now call the Big Bang, which was hot and fiery. So one of the contenders at the time was the steady state theory. So this is a theory actually proposed by Fred Hoyle. And this was the theory that he was touting to explain these observations at the same time as people were also working on the Big Bang theory. Now, Fred Hoyle was an excellent scientist. I don't have many scientific heroes, but he's one of mine. And he understood relativity very well. And in his picture, he wanted to retain this picture of expanding space because it naturally explained how things are moving apart. But he didn't want a beginning. He didn't want a beginning to the universe. He wanted the universe to appear to be the same over all times. And to do that, of course, is that if you have your theory and it has expanding space, and you want the universe to look the same over all time, then as the universe expands, matter spreads out. So you need to sort of magically reintroduce new matter all the time to fill in the gaps as matter moves apart. So he had to come up with a field that could create matter to replace the matter that's thinning out as the universe expands. Now, in terms of the observations that Hubble had, both these theories work excellently well. There is another idea which has been touted, is this notion of tired light. And this is still something that people put forward all the time as an alternative to the expanding universe model. In this picture, it's assumed that the universe is static and unchanging, but somehow light loses energy as it travels across the universe. So you need to introduce a mechanism which there isn't one in relativity, that where light actually leaks out of a photon as it travels across the universe. But in this particular picture, what you've got is you say, well, I'm going to get rid of all that picture of a beginning in the Big Bang. I'm going to have that light loses energy. And because light from further galaxies travels through more space, they lose more energy. So more distant galaxies appear more redshift than nearby galaxies. So an important point here is that these three theories explain Hubble's observation equally well. So if you're going to put forward a theory, then explaining at least one piece of information is at most a good start. And what we have is that those other theories fall over with other observations. So for Fred Hoyle's steady state theory, observations of the distant universe show that it is different to the nearby universe. So our universe is changing over time. And he basically went, he died in 2001, and he went to his grave still pushing at some level his steady state theory, but he had modified it so many different ways that it was barely an image of its former self. So, I should probably try and speed up a little bit. So fact number 3, the cosmic microwave background, okay? So this is what basically slew the tired light model. So as I mentioned, when we look at the sky, we can look at the sky with our optical telescopes. And here we have a picture of the Andromeda galaxy. We see all these blue stars, so they're young stars. But you can see that there's lots of dark patches in the galaxy, and they are dust lanes. If we switch to a different wavelength, what we see are different physical processes underway. So here in the optical image, we're seeing stars. But if I jump to the infrared, what we've got is that instead of seeing stars now, we're seeing the infrared emission from dust. So dust is this leftover debris from the life cycle of stars. And you can see that the patches that were dark in the previous image are now light in the infrared image because we're seeing where the dust is, okay? So astronomers like to gather light at all wavelengths because you see different physical processes. So if you look in the gamma ray, you're seeing highly energetic processes. If you look down in the radio, you're seeing cold gas, etc. So the question that we have is, what do we get when we look at this, the entire sky, right? So we can map out the sky over a whole range of wavelengths. So this is the entire sky on this particular projection. You can think of like the North Pole and the South Pole of the galaxy at the top and the bottom. You're seeing around the equator. This is our Milky Way galaxy, and you can see lots of those dust lanes, those dark bits. You can see lots of other stars. So we can learn a lot about the universe if we observe an all-sky view at all kinds of wavelengths. It reveals all of the processes going on. But one of the things that, again, changed cosmology was what happens if you take an image of the sky in the microwave part of the spectrum. So these are microwaves, and this emission from the sky mapped out in microwaves was discovered back in the 1960s. It had actually been predicted in the 1940s and discovered accidentally in the early 1940s, but it was discovered and understood in the 1960s. So you get to this particular set of wavelengths, and you find that the entire sky is bright in terms of microwaves. So we are surrounded by this entire sea of microwaves. The Earth is bathed in these microwaves. And in terms of the Big Bang picture, what we are seeing here is the leftover radiation from the Big Bang. So what we have is we have this, early epoch in the universe when it was hot and dense. That radiation was all bouncing around. The universe has cooled, so that radiation, which used to be gamma rays, is now down in the microwave part of the spectrum. So we can see that there are very subtle color differences. These are subtle differences in the temperature of the microwave sky, 1 part in 10 to the 5. What was important for this story, though, is what happens if you look at the spectrum of light that you get in the cosmic microwave background. So what we've got here is that the black squares are the data points. Okay, so again, this is the data. And of course, as every good scientist knows, it's not just the data point that matters, but also the size of your error bar. And what we've got in here, this is data collected by a particular satellite, measuring the spectrum of the cosmic microwave background. They're the black dots, the error bars. The error bars have been blown up by a factor of 400 to make them visible. Okay? So these are very accurate measurements. Now, the solid line that goes through those data points, that is a fit to the data of a black body spectrum. Now, again, some of you will have encountered a black body spectrum before, but this is something that was discovered by, this was derived, I should say, by Max Planck, working essentially in 1900. And what Max Planck wondered about was, if I have a scenario where matter and radiation are perfectly coupled together, i.e., I get energy flow from matter into radiation, radiation to matter, and they absolutely balance, what does the spectrum of light look like in that particular scenario? And the question he was trying to answer is, why do certain objects, you take a piece of metal and you heat it and it starts to glow, and it goes from red hot through white hot to blue hot. What defines that particular distribution of light? And what you find is that his theoretical answer is pretty good. It's pretty good at explaining things like a piece of metal, but it's never perfect, because a piece of metal is not a perfect black body. It's not in that scenario where there's a perfect flow of energy into radiation, radiation into energy, etc. But the cosmic microwave background is, okay? The cosmic microwave background is the most accurate black body that we have ever measured, okay? So what do we take away from this, right? So the CMB, the cosmic microwave background radiation, this is light coming from all over the sky. It is at this particular temperature, and that temperature is of light and matter perfectly coupled together at a temperature of 2.725 Kelvin. And there is no matter in the universe today, or no place in the universe today, where light and matter are coupled together at that temperature. Okay? Now, for Fred Hoyle, he was desperate to try and explain where the cosmic microwave background radiation comes from in his picture. And so he had this idea that the universe was filled with these crazy little iron bits of metal, and they were interacting with light in a really funky way to give you the right kind of spectrum, but it never really worked. So the only way that we can sort of make it work is that the universe once was in a state where matter and radiation were perfectly coupled. And this was like, just after the Big Bang. So the universe was in a hotter and denser state. And what we're seeing is that leftover radiation today. Now, one of the cool things about the expansion of the universe in terms of general relativity is that if you have a gas of radiation and you expand it in expanding space, it preserves the shape of the black body curve. So you just move the curve to lower temperatures, you keep the correct shape. But in the tired light picture, it doesn't work anymore. So tired light fails because it would say that the cosmic microwave background radiation should be distorted away from a black body curve. So the Big Bang sort of wins again. And the message that we try and get across to our potential revolutionaries is that facts are often numbers, and you need mathematics to make predictions, right? So, I know this audience is going to be happy with an equation. Lots of general public aren't, but of course, this is the Planck blackbody spectrum. He wrote this down in 1900. This fits the leftover radiation from the Big Bang without any tweaking or messing around. But this is what you need to have for scientists to take your theories seriously, right? You need to have this picture whereby I've got a mathematical equation and I can apply it to data. And so many, like the theories that we receive in our letters, so many of our theories are ideas where people say, if somebody would just help me with the maths, I'm sure this would revolutionize cosmology. I'm going to try and speed up slightly. I'm going to zip through this fourth one. Chemistry, right? We have this periodic table of elements, and what we want to know is, where did these come from, right? Was the universe born with 92 natural elements, or was there a process whereby these elements came into being? And our understanding of this was one of those clashes, confluences of history, right? This was the 1940s, and in the 1940s, people wanted to understand how nuclear reactions work. Now, on the peaceful side, it was for nuclear energy. On the less peaceful side, it was for developing nuclear weapons. So people could write down the equations of how nuclei interact at high temperatures and high densities, because that's what you need to do to be able to understand what happens in a nuclear explosion. At the same sort of time, some of the people, some of them who were involved in these projects as well, said to themselves, well, if our universe was in a hot, dense state at the start, a state so hot and dense that normal matter couldn't exist, then maybe we can use the same equations to tell us how our universe evolved. So back in the 1940s, there was this picture that people had about how elements get built up over time. So you have to imagine the universe was born really hot and dense. We don't know the details of that, but it was a state which was essentially free quarks, the things that make up the nucleons. They were bouncing around. It cooled for them to bind into protons and neutrons. Then we have nuclear physics, and then we try and understand the evolution of the universe from there. So we can come up with a picture that in the early universe, protons and neutrons were crashing into each other. When the universe was very young, those collisions were very violent, so the protons and neutrons would bounce off each other. But eventually you cool the universe down such that you get a proton and a neutron sticking together to give you deuterium and deuteron. They get struck by another deuterium nucleus, and that can give you helium. And it turns out that you can, if you look at this, eventually get to a point where the universe is cooled down so much that the actual Coulomb repulsion between nuclei stops nuclear burning. But in terms of understanding the universe, what we have here, I've got this nice schematic picture, but what we've got here is a network of paths, right? So here we've got a neutron and a proton, deuterium, helium-3, helium-4, tritium. They are the various nuclei, and I've got these various paths that connect them. But these are equations, right? These are equations that depend upon the density and temperature, and they tell me how much deuterium gets converted into helium-3, blah, 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 blah. So I can set up a network of equations and solve them to tell me what kind of predictions I should get for the makeup of the chemical elements in the universe. One of the interesting things to note here, this is one that has always bugged me, we start off with protons and neutrons, and we notice that we have to go through deuterium and then make all of the other heavier elements. And it turns out that in our universe, the diproton, two protons stuck together, and the dineutron, two neutrons stuck together, are unstable, right? It's only deuterium which is the stable one. So we actually have a bottleneck which basically stops the formation of elements until you get to the right kind of conditions, because you can't get protons to stick to protons, neutrons to stick to neutrons. But that is the topic of another book which we published a few years ago, available in good bookstores. So I can solve these equations, and what I've got here now is, this is the evolution of the universe. We have time across the top in seconds. So we go from 0.1 seconds up to 1 million seconds. Temperature across the bottom. And then what we've got is the various amounts of elements in the universe. So if you look on the left-hand side, when temperatures were really high, there was only H, protons, right? That's the nucleus of the hydrogen atom, and neutrons, and a tiny bit of deuterium. We get down to around 1 second or 1 to 10 seconds, and the universe has cooled down to a point where things can really start to stick together. We go for a couple of minutes. The universe has cooled down to a point where we can no longer create the elements. And what you get is that coming out of nucleosynthesis, you get that the universe is 75% hydrogen, 25% helium, than a mix of the other elements. And when we go out there and measure these, this mix of elements is precisely what we see when we look at pristine gas in the universe. Our sun is basically 75% hydrogen, 25% helium, plus other trace elements. Okay? So this explains where the primordial elements came from, but you'll notice that in here there's no carbon, there's no nitrogen, there's no oxygen, there's no stuff that makes us. So where did that come from? And I'll just zip through this quite quickly. Again, we have Fred Hoyle here, he's the one on the right, but we've got the two Burbages, Margaret and Jeff, and Willie Fowler. These guys wrote a paper in the 1950s which sorted out where the rest of the elements came from. And what they deduced is that the only other place in the universe where you can create lots of elements heavier than hydrogen and helium has to be in the centers of stars. So they worked out, again, in a star like the sun, you know, hydrogen is burned into helium, the sun will burn some helium into heavier elements, then the sun will die. But if you want to create very heavy elements, you need to have very massive stars that have temperatures and densities that can basically cook up carbon into neon, into oxygen, into silicon, into iron. And if you want to make even heavier elements, you need to come up with more extreme environments. And that's when basically these stars die, they rip themselves apart. That's when you can create elements heavier than iron. Again, all of this is underwritten by nuclear equations and the equations of gas and plasmas and gravity squeezing on stars, etc. So we can come up with our periodic table of elements now color-coded by where they come from in the universe. And we now have this overall picture that hydrogen and helium created in the Big Bang, and the other elements come from either light stars or heavier stars undergoing various processes. So the lesson here is that your physics all has to hold itself together, right? And what I mean by that is that you can't demand that there is other physics going on in the universe which is different to the physics that we have here on Earth. You should be able to build up your picture by pulling in the laws of physics and saying, look, I've now got this consistent picture for the entire evolution of the universe. So I'm going to just jump over this and get to this point and just mention that cosmology is a great success of the last 100 or so years. And when we're approached by people that want to revolutionize cosmology, they're always talking about the redshift and expansion and quasars and galaxies having discordant redshifts, etc. As if that's the place where cosmologists, you know, have nightmares. But they don't. The place where modern cosmology has nightmares has got nothing to do with the expansion and the Big Bang and all that kind of stuff, because that has got, like, essentially overwhelming evidence. It's the small scale universe. And this is just an example of where we're at. This is the thing that keeps cosmologists up at night, is that what we've got on the left-hand side here, this is a synthetic galaxy. This is a galaxy I create in a computer by taking the laws of physics where I have expansion and gravity acting over billions of years, and it creates an object which is akin to our Milky Way galaxy. And it's surrounded by hundreds of these small little blobs. And these blobs are basically lumps of dark matter that could host small dwarf galaxies. And the prediction is that there would be maybe 1,000 of these dwarf galaxies surrounding a galaxy like our Milky Way. The picture on our right is actually the scenario that we have. When we go out there and look at the number of galaxies, there's actually only tens of individual galaxies orbiting the Milky Way. So it's not solved. Cosmology is not solved because we still have these problems where we cannot get a consistent picture of how the universe has evolved to give us an agreement between our theoretical calculations from a computer simulation and our observations. But it would be really nice if one day somebody at the end of a talk came up to me and said, oh, I could solve the missing satellite problem for you. That would be really helpful. So lesson 5 is that essentially, look, it's not all solved. And so there is room for changing cosmology, but it's not in the places where people think it is. So I probably went a little bit over time there. So I'm happy to finish up here with our lessons. As I said, they're not only lessons for cosmology, but I think they're lessons for anybody looking at to undertake a revolution in science. But cosmology works really well, but it's not perfect. And I'll finish there.
Okay, thank you, Geraint, very much. That was excellent talk. And of course, now we have time for questions to Geraint. And I want to encourage first our students to ask the questions, please. So so one of the things to do in this procedure, there is the option of raise hand, and you can raise the hand and ask question, or if it's hard to do that for you, or hard to find that option, you just unmute your mic and start talking, please.
And I'm happy to take any questions about cosmology. I'll give any of them a whirl.
Okay, I think we have a first question from Joe.
Hey, yeah.
Yes, please, go ahead.
Hello. So yeah, I got a question just regarding this whole new a new model for cosmology.
Mm-hmm.
So I know that people doing I know like currently with Planck data and that we know lambda CDM is looking more and more like the model to have for cosmology. But then there's still a lot of effort on global fits, maybe in the hope of finding some like very different part of the parameter space where it just happens to fit cosmology just as well for what we know now, but able to explain more. How realistic do you think that is, that we just somehow completely missed the obvious and the real standard model for cosmology is like very far away from lambda CDM?
So firstly, let me just say that if the universe is lambda CDM, it is the most boring of universes, right? Because lambda doesn't do anything. CDM, cold dark matter that doesn't interact with baryons other than gravity, is boring. So, the search is on, as you said, for anything that hints of something a bit more interesting, a cosmological model which is different to lambda CDM. The problem is that you do have a lot of explaining to do, okay? So, as you said, you're looking for something that matches the CMB, but you also still need to be able to explain galaxies and the distribution of elements, etc. So you still need to test all of those different things. And that's one of the problems that a lot of the alternatives have, is that they fall over with some of the observations. And you often, well, I wouldn't say often, sometimes you find that the proponents of their theories are ignoring some of the observations because they can't explain them. What's the chances that we've got it horribly wrong? Well, I like to talk about this kind of stuff in betting terms, right? Because, that's what statistics and Bayesian statistics comes down to, right? How much are you willing to bet? And, maybe I'd have $100 flutter that we've got it completely wrong, because the returns would be really, really good. But I definitely think the weight is on the side that we are at least in the right kind of environment, and that we haven't got it radically wrong, but it's still there as a possible.
Okay, cool. Thank you.
Hope that made sense.
Yeah.
All right, do we have other questions, guys?
Nobody's got any questions about the universe?
Okay, I do have a question. Maybe I'll just provoke this discussion further. Look, Geraint, I agree that the many things which are related with the expansion of the universe and the background geometry, what we call, are more or less understood, and they are on good theoretical kind of basis. We've got the equations to solve and things like that. But still, there are quite significant problems. Where the Big Bang come from, and those kind of questions. You know, the singularities, and you know. So, what is your take on this?
Okay. So I will do my my cover. So if you talk to cosmologists about the Big Bang theory, what is the Big Bang theory? They will tell you that it's the evolution of the universe from just after its form to today. And the question of the origin of the universe is a somewhat separate question. So we wouldn't claim that we would be able to say where the universe came from in terms of the Big Bang theory. We'd say that there is something missing because we can't push the maths back further to work out where our universe was born. And of course, as you know, there is suggestions that our theory of everything, our grand unified theory where we have quantum mechanics and gravity working together, is the thing that is needed for us to peer through the Big Bang and work out what structure we came from. But I would say that in terms of observational cosmology, etc., that's somebody else's problem, is the birth of the universe. Similarly, the center of black holes, that's somebody else's problem. That doesn't impact the universe as we observe it.
All right. I may disagree with that, actually, in principle, because well, you mentioned inflation, for example, right? And roughly, if you explain the inflation, is just this is something which you know, the stretch it, you know, the very small universe stretch it out to a you know, huge distances, which we observe now. So and those inflationary scenarios are just at the very, very beginning of the universe, where you correctly mentioned that all these quantum effects of gravity, which we don't understand very well, you know, are expected to be very important, right? So,
yes.
And there is this expectation that, you know, these stretched kind of distance scales would imprint, for example, something which we don't understand yet. You know, and maybe the revolution is still there also to understand those structures.
That's right. But it's a maybe. But it will take a revolution in our physical theories for us to actually solve them, I think. So it's a completely separate topic, but we should do this in the pub. I get into arguments over inflation all the time because it is actually a slightly ropey aspect of cosmology, in that the problems that it claims to solve could be solved in the initial conditions rather than the need for inflation. So it is, until it gets its direct evidence, it's still there as a somewhat, I wouldn't say hand wavy, but you know what I mean? It's a possible, but not a guaranteed feature of the universe.
Yeah, that's right. Yes, so I would agree with those comments. So do we have other questions?
Hi, Geraint. This is John Byrne.
Oh, hi, John.
I apologise, I came in very late on this, so if you've answered this, sorry. Values of the Hubble constant and the apparent convergence on two different sets of values.
Mm-hmm.
Any comment on what's going on there?
Okay, so I'll just give some people a bit of background. So there's something going on at the moment called the Hubble tension. One of the things that Hubble did is he measured the expansion of the universe, and it's in a number, a Hubble constant, which is a measurement of speed per distance. It tells you how fast galaxies are moving apart from each other as a function of distance. And when Hubble first measured it, he got a number which was like 500 kilometers per second per megaparsec. He had gotten his calibrations wrong, and much of the 20th century was focused on tying down the value of Hubble's constant. And there was one group that thought it was 50, another group thought it was 100. And basically in about 1999, the Hubble Space Telescope showed that it has a value of around 70. So everyone was very happy. We'd measured Hubble's constant. But But people didn't stop there, of course, as they kept doing more and more precise observations. And we've gotten to this point where we have different methods of measuring Hubble's constant, and they give slightly different results. So one method is basically a continuation of the method that Hubble did, is you measure the distances to objects, you measure their redshifts, and you get a value there of around, I think it's like 72, 73 kilometers per second megaparsec. And there's another method whereby you can measure Hubble's constant from the cosmic microwave background. So you can use features on the cosmic microwave background to measure the expansion of the universe, and it gets a value of around 68 kilometers per second megaparsec. Now, in the good old days, these measurements were so, their uncertainties, their error bars were so big that nobody worried about these differences. But now the error bars are down at less than 1 kilometer per second in these units. So they are discrepant, and they're discrepant by a few sigma, right? So they are discrepant by enough that makes you sort of go, oh, that's interesting. And observations that use the cosmic microwave background, there's several of them, are consistently getting a low value. Observations that are using what's known as the distance ladder by stepping out of the universe, they're getting a high value. So what are the potential solutions? Now, what happens, of course, is if you have this kind of discrepant measurements, the first thing that happens is that the theorists all go, yay, new physics. And they try and come up with a physical model that could explain this discrepancy, which is different to the basic underlying model. So there are people suggesting that the expansion of the universe has undergone basically some hiccups, that something was in the early universe, something like dark energy, but has since faded away, that changed the expansion. So that was imprinted on the Hubble's constant as measured to the cosmic microwave background, but has disappeared today. So it's not seen in Hubble's constant measured through the distance ladder. So there are people just going, maybe it's new physics, and there's a lot of theoretical papers. The problem that we have is that the cosmological distance ladder is a ladder. It's based upon a series of calibrations as you move outwards in the universe. So nearby stars you can measure by geometry, the distances. Further away stars you use their brightnesses, and further away you use variable star brightnesses, and further away again you use supernova and all this kind of thing. You build up a distance ladder, and what you have is that if you make a slight error in one of your steps, then it propagates itself along the distance ladder, and that basically systematically influences your Hubble constant. So I saw, the most recent thing I saw about this was a talk by George Efstathiou in Cambridge, who claimed that you could be down at an error of, a few percent in the brightness measurements, or the brightness calibrations, propagated along and could basically account for this difference. So at the moment, we don't know. We don't know if it's one way or the other. I do know, having experienced a few exciting points in physics, that systematic errors, as they call, come and bite you in the bum if you're not careful. So, we don't know if it is one way or the other. I think at the moment, lots of people are shrugging their shoulders and saying, we need more precise measurements and we need more precise calibrations before we can say it is definitely something to do with physics, or just definitely something to do with the method.
Hey, Grant. It's Claire Edmonds. I was wondering, more of a sociological question almost. Do you think there's something about cosmology which really appeals to people to sort of design these, or really explore these revolutions and try to think of new ideas more than other fields?
So there's two things. Firstly, I think cosmology, talking about origins of the universe, is something that the broader population is interested in. But I think this notion of wanting to overthrow cosmology or to explain cosmology is related to its appearance in the press, right? It gets a lot of press. I saw somebody complaining the other day that the vast majority of physicists around the world are solid state physicists, and they never get front page headlines, but cosmology does. So I think it is related to our public face. And I think, quantum mechanics is another one that that has that public face, and so has a culture of people that are interested and possibly think that what people are doing in quantum mechanics is wrong.
Yeah, cool, thanks.
Right, more questions, guys?
Is there something on the chat there? I haven't got a mouse control here.
Yes, we've got something on chat. Can you read it? That Geraint?
I can't get to it because I don't have mouse control at the moment because I'm in
Okay.
screen. So
Jennifer is asking, hi, my mic does not work. So I have to type. I wanted to ask where you see the future of cosmology and the research for it.
Oh, future. Here we go. You know, astronomers, when asked, you know, what's the next step, it's always build a bigger telescope. I mean, what we're facing the same problem as particle physics is in that we don't really know where to look. So, you know, with the cosmic microwave background, every time we build a better telescope to look at the cosmic microwave background, we just agree with the theory better and better and better. And as Archer was saying, that maybe we need to look out in the far distant parts of the measurements to see if something doesn't quite fit. Similarly, with regards to observing the universe, you know, things seem to work really, really well. I didn't touch upon large-scale structure in too much detail, but the large-scale distribution of galaxies, all this kind of stuff, it all works really, really well. So I think that there will be a lot of focus in astronomy on the evolution of stars and gas, because that's where a lot of the complexity remains, is, you know, how gas goes from out here into stars and back out again, all that kind of stuff. That is where there's a lot of focus. But there is a growing focus of using cosmology to probe particle physics, right? So we have a growing number of people that want to use observations from telescopes to work out whether or not dark matter is annihilating, whether or not dark matter is leaking energy into baryons over cosmic history, or also, do we have gravity correct, right? There are people that think that maybe the laws of gravity need to be modified on certain scales, and that will impact the evolution of the universe, and you will only see that in detailed observations. So, you know, it's one of those things where there are pushes going on various fronts, but I think, I personally think the most exciting side will be that trying to understand the fundamental universe from our observations of cosmology.
Hi, it's Claire again. Just building on that, are there any major sort of experiments being developed that will help with the theory? You know, large hadron colliders or square arrays, or what sort of are the things that are affecting you?
We definitely have observations which are make us take a second look, right? So one of the most well known is the gamma ray excess from the galactic center, and that emission of gamma rays could be coming from something pretty standard astrophysically, which are pulsars, dead stars, or it could be coming from the annihilation of dark matter. And so what we've got is we have this emission, but the problem is that our gamma ray telescopes at the moment, they are too low resolution to tell the two scenarios apart. So I think people are pushing for trying to get more accurate observations of things like the galactic center. But there's a lot of astronomers as well now involved in things like trying to work on direct detection experiments. So there's this one going in Stall. What's it called? It's Sabre. Sabre. I'm looking at Archer. You nodding. Yes, Sabre. So this is one of the ones that's trying to do a direct detection of dark matter by having, I think it's one of these big crystal detectors, and you hope that a dark matter particle will bounce off your one of your crystal atoms, and so it will reveal the properties of dark matter. So that there are, of course, dark matter physicists, dark matter particle physicists involved. The astronomers, of course, involved, because what they want to know then is if they can measure the properties of dark matter, how does that then feed into the cosmological models? Can we then see the signature of a particular kind of dark matter on the sky? So essentially, in answer to your question, yes, virtually every facility coming online will have a line, a paragraph in its strategic plan saying that it will hunt for the signatures of dark matter, but they will all do it through slightly different ways.
Cool, thanks.
Okay, more questions? Okay, let me check the chat. All right, I don't see any further questions. So let's thank Geraint again for this discussion and for his presentation. Thank you, Geraint.
Thank you. And hopefully see some of you back on campus at some point.
Right. And tomorrow we'll have another presentation. So please sign up and we'll continue these discussions actually for almost 3 weeks. So see you.
Bye.